Okay, for magnetic fields, we had this with electric fields. Remember, we used electric fields to describe the magnitude of the electric force. Well, in a similar way, we're going to use magnetic field lines to represent the strength and direction of the magnetic field. The strength, oh, that's Gn, isn't it? That's not right. And here I'm introducing a variable, B, which is going to be the variable that we'll use for the magnetic field. It is a vector quantity, so I'll write it with an arrow over it. Sometimes I'll talk about just the magnitude of the magnetic field, in which case I will not draw the arrow over it. There are a couple of rules, similar to the ones that we have for the electric field lines, that have to do with magnetic field lines. The first of those rules is that magnetic field lines begin at the North Pole and end at the South Pole. And that's how it's drawn in the picture here. They begin at the North Pole, like here, and end at the South Pole. With electric fields, remember we had they begin at the positive charge and end at the negative charge. The density of the field lines is proportional to the magnetic field. In particular, proportional to the magnitude of the magnetic field. So, for example, right here, the magnetic field is strong, but out here it's not very strong. That's because the field lines are very close together out here and very far apart out here. All right, so a couple of different rules. I always like to throw in this third rule. This is just because the Ghostbusters. You remember Ghostbusters, right? What about the field lines? Or actually the streams, they said. Field lines do not cross. Don't cross the streams. All right, so field lines do not cross. That's not terribly important for us, but it is a true statement. All right, the field lines do not cross. They never cross one another. There's a nice PhET simulation here. I think that y'all might have actually dealt with this in the lab, if I'm not mistaken. But there's a nice PhET simulation where you can play around with the magnetic fields. Okay, now the Earth's magnetic field is due to charged particles moving within the Earth. Well, I'll show you a video about that in just a moment. But first of all, let's consider a compass. A compass has a magnet with a north and a south pole. And a nice little compass that you can make, actually, you can take a bucket of water and put a piece of wood in it. And then on top of that wood, you can place a compass that has a north and a south pole. And of course, the north pole of the compass will point towards Jack Bay, and the south pole of the compass will point towards Homa. If you're in Thibodeau, that is. Right. The north pole of the compass points towards Jack Bay, and the south pole of the compass points towards Homa. Again, if you're sort of in a pinch, you can take a bucket and add a piece of wood on top, and then put just a bar magnet on top of it. So the north pole of the needle points north, and the south pole of the needle points south. Now, if you were to imagine the Earth as a giant bar magnet, the south pole of that magnet would be at the geographic North Pole. So what I have here is a figure. This is the green is the Earth, and this magnet right here represents the Earth's magnetic field. All right, this doesn't represent a compass. It represents the Earth's magnetic field. All right, so up here where I have the northern geographic pole, this is like, you know, where Santa Claus lives or whatever. Down here I have the South Pole. This is where the penguins live. Of course, my boy always wants to know what would happen if we took a polar bear down to the South Pole, because, you know, there are no polar bears at the South Pole, which is good for the penguins because we think that a polar bear might wreak havoc on the penguin population at the South Pole. But that's beside the point. So I have the North Pole, South Pole. However, note here that the northern geographic pole is actually the southern magnetic pole of the Earth. The northern geographic pole is actually the southern magnetic pole. So if I were to take up my compass, over here, I'm standing here with my compass. Remember, the north points in that direction, towards the north, and the south points in that direction. All right. The south pole of my magnet actually points towards the northern magnetic pole of the Earth, but that's the south, at the southern geographic pole. So the point is here that the magnetic poles are different from the geographic poles. They're the opposite, in fact. All right. So the northern geographic pole, the North Pole, where Santa Claus lives, is actually the southern magnetic pole, and vice versa. The southern geographic pole is the northern magnetic pole. Okay, if you've seen this movie, I don't have this clip actually. I'm going to show you another clip, but without a paddle there. If you've seen this movie, they're out in the woods and they're using a compass, and they say, oh, there's iron in the hills, and it's causing their compass to go off kilter. That's because, of course, iron is a ferromagnetic material, and it has its own magnetic field. And in fact, the Earth's magnetic field does vary in particular places because of localized things. But the general idea of the Earth's magnetic field looks a lot like this, that it comes out, it looks like a giant bar magnet. Primarily, this is caused, there's still a lot of study in sort of the dynamo of the Earth and how this magnetic field is generated. But there's general agreement that this magnetic field is caused by moving charges within the Earth's core. I have a little video here. This is from the Discovery Channel about how the Earth's magnetic field is created, and then also how that Earth's magnetic field protects us from solar storms, from charged particles and the solar wind coming off the sun, how it protects us from that. And we'll get into that in just a bit. But for now, I want you to watch this video about how the Earth's magnetic field is generated by these moving charged particles within the Earth's core. So you can watch that here. It's just a few minutes long. There's a quick test, and then quickly I'll go here because it touched on this in the video, but the sun is always emitting vast quantities of very high charged ionized particles. We call it the solar wind. And this solar wind comes towards the Earth. Of course, there are some other planets in between, but it comes towards the Earth. And because of the Earth's magnetic field, these charged particles are deflected by the Earth's magnetic field. That's good because that solar wind can be very damaging to the atmosphere, and as I said in the video, also to the water on the planet Earth, that would basically all be gone, and we'd just be a barren and dead planet without the Earth's magnetic field. We do get one phenomenon called the aurora borealis, and that occurs when a small portion of these electric particles, these charged particles, when they will get entrained into the magnetic field and deposit on the top of the tops of the Earth on the north and south poles. And that generates this aurora borealis. I have another clip that I want to show you, this magnetic substorm which is creating this aurora borealis. And you can watch that here. All right, we will stop here and pick up a little later.